Hello everyone, welcome to Chapter 6, Modeling Random Events, the Normal and Binomial Models. In Chapter 6, we're going to distinguish between discrete and continuous random variables, which is section 6.1. And we're also going to apply a normal model to find probabilities, which is 6.2. And 6.3 is to apply a binomial model to find probabilities. But we're actually going to skip 6.3 and we're going to only focus on 6.1 and 6.2. So 6.1 talks about what is a probability distribution and distinguishing between discrete and continuous random variables. Then we're going to use the probability distributions to compute probabilities. For probability distributions, we're going to be focusing on displaying as a table or a graph. And that's going to be able to show us all the possible outcomes of a random experiment and also the probability of each outcome. So here we're going to look at probability distribution in a table format. And we're going to use the example of rolling a die. So a fair six-sided die. So I'm going to make my table. And my input is going to be all the sides of the die. And my output is going to be the probability of each. So let's think about the probability of rolling a 1 on a fair six-sided die. Successful outcomes is 1 over possible outcomes is 6. This will be the same outcome for each side. And there's my table. So it's pretty much like what we did in Chapter 5 with the sample space, except in a table format. That's the table. So let's actually use this table. I'm going to use this table to review something from Chapter 5. So let's just say that I want to find the probability of rolling a 5 or a 6. So probability of rolling a 5 would be 1 out of 6. Probability of rolling a 6, also 1 out of 6. Remember, this is an OR probability, so the probability of rolling a 5 or a 6 would be 1/3. 6. Okay, so we're going to use that same example, but this time we're going to display it in a graph. So we'll set up an X and Y axis. My input will be on the X axis, which was the number of spots on the die. And then for my y-axis, I'm going to label this probability. So because they each have the same probability, which was, remember, 1 out of 6, usually in a graph, they'll display probabilities as a decimal or a percent. So I'm going to change this 1 out of 6 to show 0.17 instead. So when you graph each probability, it's basically just going to be a dot on the outcome and a line up until that point. Super simple graph. Nothing really complicated about this kind of graph. There's the graph of rolling a die. So when we talk about probabilities, there's two different types. The first type is discrete. In a discrete probability, it's numerical values that you can list or you can count. Example here says number of siblings, number of songs, and an MP3 player. So your hint is actually like when it says the number of. Discrete probabilities, it can be counted. So that's why this, when it says the number of, is a big hint. Continuous probabilities cannot be listed or counted because they occur over a range of values. Example is the height of a basketball player or the weight of a sandwich. So here's your hint where it says height or weight. You can think about it this way. Continuous variables are a measurement. And discrete variables are not. They're counted. Another way you can think about it is discrete. I could count the number of stairs here versus continuous. It's over a range. I can't count on that one. So it's really important to distinguish between discrete or continuous because how you graph these are going to be different. So let's do some examples so that we can kind of determine whether we're talking about discrete or continuous variables. So number 1 says the number of cars owned by a household. Well, where's the hint? It's talking about the number of cars. Could we count the number of cars a certain household has? Yes. Therefore, this is discrete. Number 2, the number of pets owned by a student. Could you count or list how many pets a certain student has? Yes, so this one's also discrete. Number 3 says the time it takes a worker to commute to a job. We're talking about time in this example where you can't really count it. Like you can't list all the possible times. So this one is continuous. It's happening over a range. You can't list it, meaning like the time it takes a worker to commute could be, I don't know, 10 minutes and 26 seconds. It could be 10 minutes and 29 seconds. There's just like a whole range of time that we could have, and you couldn't just list all of them. Okay, so number 4, we're talking about the height of a building in downtown San Francisco. Again, this is a measurement. It's not something that we're going to count. So this is continuous. There's 2 features of a probability distribution, which is basically the same thing we went over in chapter 5. First thing is all probability values must be between 0 and 1. And the second is that the sum of all probability values must equal 1. So remember when we talked about chapter 5, probabilities can only be from 0% to 100%. There's only 100% of something likely to happen. It's not going to be beyond that. Here's example 2, creating a probability distribution. Suppose you roll a fair 6-sided die. You win $10 if you roll a 5 or a 6. You lose $5 if you roll a 1. And for any other outcome, you win or lose nothing. So create a table showing the probability distribution for the amount of money you will win playing this game. In this example, there are 3 possible outcomes. Win $10, lose $5, or get nothing. So here's all the 3 possible outcomes. So the first one, the probability of rolling a 5 or a 6, that would be probability of 5 or 6. Probability of rolling a 5 would be 1 out of 6. Probability of rolling a 6 is also 1 out of 6. So this probability would be 1/3. Same example we did before. The second outcome is the probability of rolling a 1. This is when you lose $5. So what's this probability of rolling a 1? 1 out of 6. And then the last outcome is the probability that you win or lose nothing. So this is all the other numbers, which is a 2, a 3, or a 4. Which would give you 1/2. So we're going to list all those outcomes in this table. So the first outcome is losing $5. This was outcome of rolling a 1, which is 1 out of 6. The second is if we win or lose nothing. So that was the probability of rolling a 2, 3, or a 4. And that was 3 out of 6. I'm going to leave it unsimplified for now. And then the last outcome is getting $10, which would be rolling a 5 or a 6. And that came out to 6. So the reason why I'm showing this with unsimplified values or fractions is to show that when you add these up, 1 plus 3 plus 2, we get 6 out of 6. What is it equal to? 1. So the sum of all of your probabilities in a probability distribution needs to equal 1. If it doesn't equal 1, then it's not an accurate distribution because something's missing. And as you can see, I am able to list all of these possible outcomes, which tells me that this is discrete. So now we're going to talk about distributions for continuous random variables. But because you cannot list all outcomes for a continuous random variable, we cannot represent the distribution using a table. We're only going to be focusing on graphs for continuous probabilities. These graphs are called probability density curves. This is generally what a probability density curve looks like. We're going to be later on focusing on normal probability curves. And so if you look at this curve, no matter what, everything under the curve is 1 or 100%. We're going to focus on finding the probability of just a portion of that area under the curve. So we're basically going to be finding the area of part of it. We're not going to use calculus because normally we could use calculus to find area under a curve, but we're going to be using statistical techniques to find a certain area. So here's example 3, finding probabilities of uniform distributions. Eric wants to go skiing tomorrow, but only if there are 3 inches or more of new snow. According to the weather report, any amount of new snow between 1 inch and 6 inches is equally likely. The probability density curve for tomorrow's new snow depth is shown. Find the probability that the new snow depth will be 3 inches or more. So looking back at the problem, I'm going to point out something where it says right here that it's equally likely. So equally likely, this is a uniform distribution. So that's why this graph doesn't have a curve, because all of the snow depths have an equal probability. So the question saying that according to the weather report, any amount of new snow between 1 inch and 6 inches is equally likely. So looking at your graph, you notice that your x-axis goes from 1 inches to 6 inches. It's questions asking, find the probability that the new snow depth will be 3 inches or more. So we're going to be finding the area of this portion of the graph. So I'm going to go back and highlight the part of the graph again that we're trying to find the area of. And remember, we're looking for 3 inches or more of snow. What's this probability? The area of a rectangle, if you remember, is either length times width or base times height. So we're going to find the area of our shaded region, which is a rectangle. So the base of our rectangle is 3. And then the height is 0.2. 3 times 0.2 is 0.6, or in other words, 60%. If you notice, 60% of this rectangle is shaded. So when you look at this uniform distribution graph, you might be wondering, how did they get this 0.2 value? So I'm going to show you how they got that. I'm going to go back to area is base times height. Well, what do we know about the entire area of the rectangle, the whole rectangle? Well, we know that the probability is going to only be up to 1, so the entire area can only be 1. The base of this whole rectangle we know to be 5. 1, 2, 3, 4, 5. And the height right here, 0.2, I'm going to label H, so I can show you how we're getting this 0.2. So I'm going to solve for H by dividing by 5. 1 divided by 5 is the same thing as 0.2. So the values on your y-axis is always determined by knowing that your area is 1. And I just wanted to show you that because you're not always going to be given those intervals on the y-axis. Sometimes you might have to figure them out on your own. So we just went over finding areas for uniform distributions, which will be rectangles. Sometimes when we find area under a curve that's not a geometric shape like rectangle, it's a little bit more difficult. But just to be clear, we're going to be finding these probabilities manually, not with computer-based technology, because well, the computer could just like magically give you the probability, but I want you to understand how it comes about. So we're not going to use computer-based technology, but just to give you a heads up, what we're going to be doing in the next section is we're going to be looking at a normal curve, and then we're going to be finding the area or probability of part of that curve.